it's the snowmobile problem. Okay, this is number one, starting with the alphabet soup of the snowmobile problem. So I'm gonna have to erase some of this work. So hopefully y'all have it from somewhere else. This is all different problems. So I'm gonna get rid of the DVAT and all this. Okay. So I'm gonna read the question. So I figured that would be helpful. Snowmobile on a frozen pond is moving at 15 meters per second, while when the driver decides to pass a slow-moving sled, if the driver accelerates to a speed of 19.5 meters per second in a time of 4 seconds, what is the acceleration? Okay, so we've got the guy, this is a snowmobile, and then at the end, the snowmobile is going faster. So I'm going to draw an arrow. My velocity is 15 meters per second. Then I'm going to draw a bigger arrow, and the velocity is now 19.5 meters per second. And it says that we did this over a time period of 4 seconds. What is the acceleration? Okay, we have kinematic equations to be able to solve for this, so okay, so the one we're going to use is VF equals VI plus AT. And we have 3 of these. We're just going to plug in the 4th one. The final velocity is 19.5. The initial velocity is 15. The acceleration is, the acceleration is I don't know. And the time is 4 seconds. So do some subtraction. I think that comes out to 4.5 equals 4 times the acceleration. 1.1? Okay, so the acceleration for that one is 1.1 meter per second squared. I'll write that over here because that'll probably be helpful to us. Okay. Yeah, the initial velocity would be starting at 15 meters per second, and the final velocity would be ending at 19.5 meters per second. It happens. We all have our moments where we get things backwards. It totally happens. The neat part is whenever you can go back in and double check it, because if you did flip them, then you would get a you would get a negative time, yeah, which would be kind of weird. Or I'm sorry, you would get a negative acceleration. We were solving for acceleration. Uh, and as long as you know that you're having a positive direction, you can be like, wait a minute, that's not right. You can go double check. And when you erase this, we're gonna move on to part B, because I gotta have more room. So I'm just gonna erase it. Good news is now that I'm actually recording it this time is it doesn't really go away. We can just look at the videos. What distance will be covered by the snowmobile in the time it takes to accelerate? Use the values from part A. Okay. So now we're looking for the distance. You want to use the 4th forbidden equation? Forbidden equation. Distance equals VI plus VF divided by 2 times time. Okay, this would be completely ignoring the acceleration, which is fine because the VI plus VF over 2 is the acceleration in this case. It's the substitute for it. So we can use this. We have it. So that's the VI of 15, the VF of 19.5 divided by 2 times the time of 4 seconds. And whatever that comes out to be, that's our distance that was traveled, our displacement. But since since we're always going forward, it's the same as the distance. 69 meters? Yes, 69 meters. Okay. 69 meters. Aw, typical teenagers. Okay, 69 meters for part B. Nope. Looks to be correct. 69 meters. Part C. Oh, this is like a completely different. Did they just like change it completely? Yeah, it's not even really related to the snowmobile part anymore. So it looks like this is a complete different one. A wagon is initially moving up a hill with a velocity of 4 meters per second. The wagon is accelerated down the hill at 0.64 meters per second squared until its final velocity is 2.3 meters per second down the hill. Calculate the displacement from the initial position. Okay. So we have two situations, and we can do this one of two ways. I guess since we're going up a hill, I'm going to go ahead and just draw the hill because it's a good time to go ahead and talk about the concept of the line of action. So here's a car, and here's the wagon on the other side. It's a very sleek station wagon. Um, it's going up a hill, right? I didn't hear the question. Yeah, it's a regular wagon. Yeah. I thought it was a car. Never mind. There you go. It's a regular wagon. Um, so since it's moving uphill, sometimes people get confused, but this is really just a one-dimensional motion problem because you can draw a straight line between both of the locations, and that's the same thing as if they were flat on the ground. So that dotted line that I'm drawing right there, that's something called a line of action, and we're going to be using that a whole lot in the next chapter. Um, but that's the reason why I can make this a one-dimensional motion problem is because it's technically not really moving anywhere outside of the line of action. Yeah, it was, yeah, basically. So, like, if you've kicked it up the hill, so like at the very beginning, it would have a speed to it, and then it would start slowing down further as it made it higher up the hill. So, we have a, let's write out our DVAT. So, D, VI, VF, A, T. Let's see what we got here. Because I think this is one whole situation. I don't think we have to break this up into two separate situations. What is the total displacement? Unknown. Okay, I don't know. What is the initial velocity? 4.6. I'm going to put meters per second, and I'm going to put that up here too. So 4.6, just to kind of give our picture some context. VF, because it's going down, right? So it eventually gets to where it's going down, negative 2.3 meters per second. So I'm going to draw that the other direction, negative 2.3 meters per second, because it will slow down and then eventually it'll start going down the hill. Since, yes, since it says the acceleration down the hill, that down is telling us that we're going to be going in the negative direction. So everything up the hill is going to be positive, and everything down the hill is going to be negative. So the acceleration in this case is negative 2.3 meters per. No, wait, hang on. I'm lying. I'm lying to you. What number is the acceleration? Negative 0.64 meters per second squared. Do we have a time? Okay, so we don't have time. We don't have displacement, but we have VI, we have VF, and we have A. So the initial position would be right whenever we photographed it at 4.6 meters per second. So we're looking for our displacement from here to when it makes it to its negative 2.3 meters per second, which means it's going to go to this point, go up a little bit higher, and then come back down. And what we're looking for is here. But we don't have to break this up into two different parts because the delta V, the change in velocity, since it's positive and negative, the kinematic equations will automatically take that into account since it is undergoing a constant acceleration. If the acceleration did not change, you don't really have to break it up. There is a way that you could do it in one step. And in this case, I would rather do it that way. I would rather do it in one step. So, um, do you want to solve for the time first, or do you want to solve for the displacement first? Actually, it's only asking for the displacement. It looks like part D is a completely different one. So if we can just solve for displacement, our job will be easier. Is there a kinematic equation that we can use that would just solve for displacement? Okay. Is that I think that's the second one, right? VF squared equals VI squared plus 2AD. We do have acceleration. We have VF and VI. We can solve for this one and just be done with this problem. I think that's fine. I would do that. So VF is negative 2.3 quantity squared equals 4.6 quantity squared plus 2 times negative 0.64 times the displacement. And now we got to do a little bit of number crunching. You got the whole thing? Okay. I'm going to write down a couple of things for my digital people. The 2.3 squared is 5.29. The 4.6 squared is 21.2. The negative 0.64, I probably don't need to put this in the calculator, but I want to make sure, times 2, 1.28, and that's a negative, so let's just write minus 1.28, 8 times displacement. Subtract the two onto each other. So this is negative 16.01, correct? And that's negative 1.28. So we divide the two onto each other. Did I mess up? Uh-oh. Up here? Okay. I'm going to take y'all's word for it. So negative 15.87. So we're going to divide those two onto each other. Negative 15.87 divided by negative 1.28. And you get a total displacement, 12.4 meters. And that would be your answer. Okay? If you calculated this, if you ran through the kinematic equation and you made the you made the final velocity 0, you would actually come out with a larger displacement, and that's because if the final velocity was 0, you're going to be more towards where this plus sign is up here. Okay? Didn't realize that that was actually on. Go back to no touchy. Okay? No touchy. D is different, right? Completely different problem. So, okay, I'm going to erase these. Completely different problem. So I'm going to erase these. And means I got to get rid of my picture too. We'll go for part D. Your friend is on a quad and I guess it's like a four-wheeler, and is moving at 14 meters per second when you breeze by on your bike. Apparently the quad is not doing a very good job, or your bike is moving really fast. Your friend accelerates to 2.0 meters per second squared for 3 seconds. How far does she travel during this time? Okay. So, we have a couple of things. So the friend is moving, and then the friend is going to try to catch up to you. So there are a couple of numbers here. There's a 14.0, there's a 2.0, and there's a 3.0 seconds. So let's take those, and let's see if we can put that into our DVAT. So do we have a distance? No. Do we have an initial velocity? Sure. They're moving 14 meters per second, right? Okay, and they're moving that way. So I'm going to write 14 meters per second. Do I have a final velocity? No. Do I have a acceleration? Okay, So we have an acceleration, positive or negative. So we know that they're going to be going faster, but we don't know what the VF is. So it's positive 2.0 meters per second squared. Do I have a time? 3.0 seconds. Okay. Okay, we do not have displacement, we do not have final velocity, and they're looking for how far we're going to travel. So if we can find a kinematic equation that can solve for distance without having final velocity, our life would be nice. The third one? The third one? Okay, let's write it out and let's see. Write the third one. D equals, tell me. Okay, there is a 1/2, that's true. There's a 1/2. Tell me. VI. VIT, good. You are correct. Yeah, VIT plus 1/2 AT squared. Displacement equals VIT plus 1/2 AT squared. Big brain time. Uh, I I think that this one is the hardest one to remember, to be honest, because it's got that. It's almost like a whole quad. It is a whole quadratic. It's not almost a whole quadratic. It is. So I think we have everything. So D is equal to 14 times. Is that 3 seconds? Yeah, 3 seconds plus 1/2 2 3 squared. That actually, well, these will actually, aside from 14 times 3, that one kind of scares me a little bit, but we'll be okay. 9 times 9, or 3 times 3 is 9. 9 times 2 is 18. 18 divided by 2 is 9, so it's plus 9 there. 14 times 3, what is that? 30, 40, 42? Okay, so it's 42 plus 9 is the distance. I think that's it. 51? 51 meters is the total distance that we traveled using the third kinematic equation. Good. Does the next one actually count as a vehicle? I don't know. Is an oil tanker a vehicle? It is? Okay. I thought it would be more like a vessel than a vehicle, but yeah. I don't know. What's the difference between a vessel? Yeah, yeah. Let's just do the problem. Oh, you mean like an oil tanker is in like the 18-wheeler? Okay. I was thinking like a ship. Okay, tanker truck. They should call it a tanker truck then. Gotta erase this. Okay. We have information, so I'm going to highlight the important numbers. Tanker traveling at 18 kilometers per hour. Oh gosh, we need to convert these. 21.6 kilometers per hour. The acceleration is 0.2 meters per second squared towards the east, so that's going to be a positive acceleration because it's going right. Compute the total displacement from the tanker's initial position. Okay, so we have an initial and a final speed. So the initial 5 meters per second. The final is 6 meters per second. So it is going a little bit faster on the, I'll draw my exaggerated arrows. It is going faster afterwards, okay, which makes sense because it's got an acceleration of positive 0.2 meters per second squared. So let's make our DVAT. DVAT's our friend. And when y'all get better at this, you might not necessarily have to put in the DVAT, but while you're starting this, I would highly recommend you do it because it really kind of guarantees your ability to place the right kinematic equation and not guess and check. The worst thing to do is like try to start working the wrong equation and then you have to start over again. I'd rather just write the DVAT out first and make the right choice. Do we have a displacement? Okay. Do we have an initial velocity? What is it? 5? Okay. Do we have a final? 6. Do we have an acceleration? Yeah, we do. 0.2 meters per second squared. Do we have a time? No, we do not have a time. So, all right, we're looking for it. Third. Do we wait. Yeah, I agree. I agree. We do not have time, so we can't use the third one because we don't have the time. No, you're not stupid. Uh, we do just need the displacement. Second one? Um, VF squared is correct. Equals VI squared plus 2AD. That is the correct second kinematic equation. Very good. Okay. I know y'all are actually like getting these equations down and you're not like having to stare at them. It's good. I'm surprised when people learn like anything, to be honest. So it's good. It's always a good thing. It's always exciting when people learn. So 6 squared, 5 squared, and 2 times 0.2 times d. All right, just ignoring the units. 36. Okay, 25 plus 2 times point 0.4. Yeah, 0.4d. Good fix. Good fix. 36 minus 25 is 11. Well, at least I don't know, it doesn't look like it's going to turn out very nice, but what is 27 and a half? Okay, 27 and a half meters. That's it. We're good. So that one is 27.5 meters, and you're good to go. Okay. Um, and yeah, like whether you want to write the DVAT or not is a personal choice. It's up to you guys. If I look at your homework and you don't have DVAT, I'm not going to have an instant aneurysm or anything. But it is a good idea to have if you guys are just starting off these problems, especially if you ask yourself, I don't even know where to put stuff. So if your question is, I don't even know where to put stuff, then you definitely want to write out your DVAT. That way you know where things are. I understand. That's me. I'm erasing things but you know what? The good thing about me is I don't have to turn in my homework assignment. I just do the problems, then I'm done. So I can erase it and I'm fine. Y'all not so much. I need the whole thing. Love to have the whole thing. All the whole thing. Everything. Right. How do I even remember the ones that we did in class though? Like you're expecting me to remember. Oh, you want me to go back and watch all the videos? Yeah, I'm not doing that. A Corvette can accelerate during high speeds at about 2 meters per second squared, which is a pretty good acceleration. That's healthy. At this rate, how long does it take the car to accelerate from 80 kilometers per hour to 160 kilometers per hour? Yeah, it looks like we're going pretty much from about 40 to 80 miles per hour. So let's get that in meters per second, though. So Google me this. All right, 22.2 meters per second initially, and then we're going double. So 44.4. Okay, meters per second. That's our Corvette. It looks like a dot. It's fancy. Yeah, that's all you need. Don't need anything else. Okay, so do we need to DVAT or just go? Let's just go. Okay. We have VI, we have VF, we have acceleration. I need a equation. Do we have time? We need time. Okay, so time is a question mark. That means that there are two of the three kinematic equations that have time in them, and okay. So, and one of them only has displacement instead of time. So we want VF equals VI plus AT. Does this give us everything that we need? Okay. VF is 44.4. VI is 22.2 plus the acceleration is positive 2 meters per second squared times the time. Okay, that seems reasonable. Subtract and then divide, and we're good to go. So we're going to take away 22.2 on both sides. There's 22.2. Comes out to be 22.2. It's equal to 2 times time. So it looks like our time comes out to be 11.1 seconds. So you can roughly double your speed in about 11 seconds, which honestly I think a Corvette can do better than that. I don't. I think it's either an old Corvette or they're just chilling. Yeah, because I think you can reach accelerations in a Corvette more like around 3 to 4 meters per second squared. I don't think you can actually get up to gravity acceleration. I don't think you can get to 1G, but you don't need to. That would be scary. Yeah, I don't know. You just accelerate so fast, it just slams you into the back of your seat. You feel like you're laying on the ground because you're just like accelerating that fast. I don't know. Snow. Next one is completely different, right? Snowmobile, another snowmobile. Okay, so I'm gonna erase this one. That last one was 11.1 meters per second. We don't even know what a snowmobile is down here. Like we see this and we're like, what? Snowmobile? What is that? That's like a winter four-wheeler. 11.1 seconds. Okay. Initial speed. So it does have an initial speed, 5.6 meters per second, and it goes to 24 meters of distance in 2 seconds of time. Make a quick little sketch. We don't. That looks like we don't know the final velocity. Uh, 5.6 meters per second. The final velocity is, I don't know, so I'll just write VF. We're not. We'll just answer in meters per second. We'll be okay. I don't think there's anything wrong with that. Um, okay. DVAT or not? Don't need it? Okay. Well then, do we have an acceleration? What is it? Okay, we don't know? Okay. Do we have are y'all sure we don't need the DVAT? Do you have a time? Okay. 2.0 seconds. You have the forbidden fourth kinematic equation. Is that what y'all want to use? Okay. So it's in. Okay, so that's fair. Distance, and it's in red because it's the forbidden one. Vi plus Vf over 2 times time. All right, that is available, but not on the formula sheet. So we do have the distance, don't we? The distance say that it's 20 meters. 20, right, 24 meters, right? I was just seeing if y'all are paying attention. 24 meters. Um, VI is 5.6 plus VF divided by 2 times the time, which is 2 seconds. Okay. The 2's do cancel out. That's the smartest thing to do, yeah. Is you see that we've got divided by 2 and we've got 2 seconds, so you can go bye-bye. That is nice. Yeah, because you're going to take away 5.6 on both sides. So your final velocity is going to be 15.4. Oh my gosh. 18.4 meters per second. I think that's reasonable. 18.4 meters per second. Already? You're already like one step ahead of me? Well, you got distance, you got accelerate. Yeah, you got accelerate. It gives you the acceleration, so I don't think that's gonna work. Yeah, maybe I can squeeze that in one spot. If we're not using DVAT, I might be able to squeeze that one in down here. Motorcycle with a speed of 2.2 meters per second accelerates at 3.6 meters per second squared and covers a distance of 12 meters. What is the final speed? Okay, so motorcycle. We are initially going, does that say 22 or 2.2? 2.2. We're going slow to start with. And we are accelerating at 3.6 meters per second squared. And doesn't give us the final, does it? Does give us a distance. So the distance between the two is 12 meters. Okay. What is the final speed? We're looking for VF. This guy over here. Final speed on the other side. Um, you want to use VF, use the second one, VF squared equals, you're not making me write this down for nothing, are you? VI squared plus 2AD. Do we have everything we need? Okay. 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 So we have final, we have initial, we have acceleration. Wait, we don't have the final, but we do have distance. Okay. So we have everything. We're gonna have to pay careful attention that we don't take the square root of a negative number though, so be careful there. I'm gonna go ahead and write that out. VF squared equals, the VI is 2.2 squared plus 2 times 3.6 times the displacement of 12. That one is not so nice to us. Looks like we're gonna have to do some, yeah, calculator crunching here. So 2.2 squared is something. Okay. Well, let me crunch these numbers out. 2 times 3.6 times 12. That's 86.4. And we're going to take the square root of the sum of those two numbers. So 86.4 plus 4.84, 91.24. We're going to take the square root, 91.24. And that means that VF is going to be equal to the squirt of the answer. 9.56, you said? 9 point, okay, you just went 9.6. Do you go into the tens place, just like I want you to. Very nice. 9.6 meters per second. Very nice. Think we can squeeze one more in? I think we can. I think we can do it. I'm going to erase, if y'all are okay with that. So we're going to go 9.6 meters per second. Okay. Erasey, erasey. What kind of vehicle we got this time? Oh wait, a hockey puck is not a vehicle. We'll have to go with it though. I love physics problems where they just make up random crap. I mean, like who gets paid for this kind of stuff? I mean, seriously. I want that job. That's the one I want. I want the job where I just like make AP physics questions and just torment students all day long. Hockey puck initially traveling to the right 34 meters per second. Slowed down by rough ice at a rate of 2 meters per second, also known as meters per second squared. It moves for 7.2 seconds before finally coming to rest. How far did it travel? So we're going to look at our DVAT. Our hockey puck is originally, because it says it went to rest, right? So what's the final velocity? 0 meters per second. And the initial velocity is 34. So it's going fast. About 70 miles an hour. And it's slowed down by ice. And the ice is making it decelerate. DVAT or no? No? Okay. Well, okay. So we've got the numbers here. So this is time. This is acceleration. This is VI. Okay. So we have VI, VF, A, and T. And we want to try to find out how far it traveled. So which one? You want to use the forbidden one again? D forbidden equation. D equals VI plus VF over 2 multiplied by the time. Looks like it'll work. But if you want me to be honest, I think there's several of them that would work. They gave you a lot of information in this problem. So you could actually pick a different one and it would work too. The distance is what we're looking for, so d equals 34 over 2 plus, sorry, times the time, and the time is 7.2. Okay, so it's just 34, and the VF is 0, so I didn't even write it in there. So take those three numbers. Yeah, and 17 times 7.2 is 122.4 meters. Got a second on that? Yes, got a third too. Good. All right, fair. You could have also solved this using VF equals VI plus AT. That would have worked as well. Do you get the same answer? What do you mean? Why not? There's not. Oh yeah, you're right. Yeah. So if you did that one, you wouldn't actually solve what you're looking for. Let me let me try again. You could use distance equals VIT plus 1/2 AT squared. It is longer, yeah. So it would still get you to the same answer, but it would take more steps in order to be able to do. But it's doable. Anyway, that's the number two. I guess we'll have to talk about the other ones tomorrow because I think we're out of time, right? We don't have a whole lot of time left, or am I just crazy? We get out at 48, so I don't know. Maybe I can cram them in because I think y'all just wanted to kind of talk about them. Yeah, we got 5 minutes to save the world because that's the number 10 and the number 5 Superman. So let's see if we can go to number 10 and number 5 Superman. I'm gonna go down there. So this one, the water rocket, and it says that they're both launched with a speed of 30 meters per second. Determine the maximum altitude reached by the water rocket and determine the maximum altitude reached by the solid fuel rocket. Write out your DVAT for it, but there's masses here. And the most important thing I need to tell you guys right now is the mass doesn't matter. Just like how you have two things that drop, they drop at the same speed. So if I take a golf ball and a brick, both of them will fall and hit the ground at the same speed. If you are launching two things up in the air and they are being launched at the same speed, they're going to reach the same height. Now, it will take more force to get the 1200-gram thing up in the air than it is the 200-gram thing. But if you manage to get them both going the same speed, they will both reach the exact same height. So the mass here doesn't matter. The mass is irrelevant. They're just trying to confuse you guys. So the way that you would determine the maximum altitude is writing out your DVAT. The D is, I don't know. The VI is 30. The VF is 0. And the T is, I don't know. But I do know, oh, that's not a 0, that's a question mark. Sorry, that's looks like a cloudy squiggle there, question mark. But we do know the acceleration is negative 9.8 meters per second squared because we're on Earth. So you can use an equation on your DVAT to be able to find um, the distance, the maximum altitude. Okay, which equation will we use? One of the three or the forbidden one? Does the forbidden one work? Okay, so the forbidden one is out. We have to solve for t? Okay, so yeah, you can use VF squared equals VI squared plus 2AD. And I think we have enough information for that one. I'll let y'all run that one out because it's 10:46 and I need to try to at least talk about the Superman one. Superman is flying with an initial velocity of 33.5 meters per second when he decides to slow to 10 meters per second at a time of 8.05 seconds. He then continues at this velocity for 12.4 seconds before accelerating at 2.35 meters per second until he reaches a final velocity of 23.8 meters per second. Calculate Superman's displacement at this time. Hint, the motion has three unique parts. Yeah, so this is three problems in one. So yeah, when we start off with the Superman problem, this one we'll have to tackle tomorrow because there is not enough time to be able to handle that with the time that we have left. So there it is, such as it be. We'll try to wrap up kinematic equations tomorrow and start some two-dimensional motion. Maybe do a lab. I don't know. We'll see what happens. In the meantime, have fun.